All right. So welcome to our talk. We have we are happy that you are here, even though this is the last slot. So a lot of people already left or in the other rooms. And, we will present the Reactive Interaction Gateway. But before we do that, we want to introduce ourselves. This is me. I'm Kevin Bader. I'm with Accenture Technologies, based in Vienna. And
yeah, I'm Dominik Wagenknecht. I took the picture, so I'm not in the picture. One of the team events on the Danube. I came up with the entire idea of the rig. So if you think the idea is plain stupid, blame me. If the implementation is bad, blame him. So what is the idea behind it? It's pretty simple, the business pitch. As a user, while on the site, I want to do specific things and I want to see specific things happen. I want to see that my online banking, for example, pops up new transactions or new messages or stuff like that automatically. If I'm on a hotel booking site and I'm looking at a specific hotel and I'm leaving the window open and I go to the toilet and I come back again, then I want the state to be up to date. I don't want to click on a room that is actually no longer available. Or I want to choose a flight or a seat on a flight that is actually available. So in the end, it is about having real-time information available so that you can do real-time interaction. And this is particularly complicated once you go into state-of-the-art microservice architectures. And with that, I leave you with Kevin essentially, but can of course help then with all the questions that you have about why this idea is good or not good.
so now the business side is easy to describe. I want to talk a little bit more about the technical side and the motivation for it. So what is the Reactive Interaction Gateway? So let's start with a very simple example of a client-server system where I have just two devices of one user. She's Alice, and we have one backend. And we have in this example, we have synchronous request-reply through an API gateway, pretty straightforward. If we want to have notifications or asynchronous events pushed from the backend to Alice, we can do this by using something like WebSockets or server-side events. We can just make a channel directly from the backend to Alice, basically, through the gateway. So this looks easy enough. But what about if we add more services to it? So instead of having one backend, let's consider having multiple services on the backend side. This might be multiple different services, but also maybe one service that just scaled out. So if we have this and we want to get the notifications, we can do the same thing as we did before. We make a connection to this service, and then the service, or two connections basically, for each device one, and then this service can push down notifications again. But if we're interested also in events of another service, we can do the same thing again, and it already starts to look pretty crappy. So we don't really want this kind of architecture, because it's just not scalable at all. So what could we do about this? We could add a service that holds all those connections for us. That service is here. You see that all the connections go to that service, and this service holds all the connections to the front ends. So we have decoupled that. One thing that's still coupled here is that all services are coupled to this service that consumes the event from the backend services. So we can add yet another thing, some event broker. In our case, we chose Kafka, that is used to decouple those backend services from that service. And this service then basically is a Kafka group consumer. And now it's easy to show what rig is. It's exactly the combination. Like rig is an API gateway and also a consumer to Kafka and pushes down events to front ends and holds all the connections for your services. So now that you know what rig is, I want to talk a little bit more about how it works internally and its features. Regarding scaling out, rig is pretty easy to scale out. Despite holding all those connections and being stateful rather than stateless, you still can just deploy it many times, and it will synchronize automatically between all the instances among the cluster. Routing messages, you can have a lot of users, And each user either is not online at all or has one or more devices. And those devices are connected to any node. Usually you would have a load balancer in front of your rig nodes. And so you can't really know which devices are connected where. So to show this, I have in this example 2 users now, Alice and Bob. Both have 2 devices connected to different instances in the rig cluster. And then if you have a backend that generates a message for Alice, it sends this message to a Kafka topic. And then this message is consumed, in this case, by rig 3. They are group consumers, so they split, the partitions are assigned evenly among the cluster. So this is just basically at random where this message ends up. Now rig 3 knows where Alice devices are. So rig 3 can distribute the message to the other nodes where Alice devices are really connected, and those nodes then push down the message. There is another scenario where you have privileged user. We can say that Bob is privileged and is able to see all the messages, including those targeted at Alice. Then finally we have request authorization. Rig checks the validity of tokens. We're using JWTs. And we check the validity for proxy requests, so the usual API gateway thing, and also for long-running connections. So also we also have a feature for blacklisting tokens for immediate logout. So what you can do is you can, if for instance you think that something malicious is going on and you want to disconnect all the devices of a certain user, you can use an API of can use one of Rig's APIs to blacklist the token of that user, and all connections will be immediately toned down. This is special because usually with JWTs you have just timeouts, which tell you the validity of a token, but you cannot end the validity of a token before the timeout unless you have something like a blacklist. And this blacklist is also distributed in memory among the cluster. So you register JWT to be blacklisted at one node, and this information will get distributed eventually consistent among the cluster. So to summarize, rig is a stateful component, so that your microservices don't have to be stateful. It holds all the connections to the front ends and exposes internal events in a scalable way. And on top of that, it does request validation and manages this token blacklist I just mentioned. So now that we know what the features are of Rig, let's talk a little bit about how we implemented this stuff. We didn't go for Java, but instead went for Elixir Phoenix, which runs on top of the Erlang virtual machine. The reason for this, actually there are quite a few reasons why we did that. The first one is that the Erlang VM gives us soft real-time guarantees. This means that soft real-time in this case means that the average latency of any request doesn't change that much. You always get the result in the same time, regardless of how many connections you currently have. And this is possible because the actor model is implemented in Erlang VM in a way such that all actors are really very much isolated from each other, to the point where you have a separate garbage collector for each actor. Those actors' processes are not real OS processes. They're not even real threads, but are even more lightweight abstraction, which takes very little memory and can be created and destroyed basically instantaneously. So this is perfect for handling a lot of concurrent connections. You never run into a GC pause or anything like that. Then we have this distribution thing where we have location-transparent communication. The message routing I mentioned earlier, in Erlang, it's just the same thing as if you would route a message to the connection on the same host. You don't really, it doesn't make a difference from an implementation perspective. The Erlang VM is also a very mature VM. It's used in production since 1992, so it can be considered battle-tested. And it is optimized for the actor model. So with Scala and Akka, we have a similar model, but the JVM is just not that optimized for it. Then last but not least, we have reliability. The reason is that transient failures happen all the time, and Erlang has supervisors that help with this. And I would like to demonstrate this really quickly. So here you see a shell where I start the server, and a shell where I start the server a second time. And you see a lot of errors here, because I haven't started Kafka yet. I will do that. So Kafka is going up now. And if everything works all right, we should see them reconnect. So while I'm waiting for the reconnect, now you see it. They recognize that Kafka is up now, and partition 0, I only have one partition in this example, got assigned to the first rig instance. And then I connect the remote shell to the instance, and then I can start an observer, which is just a fancy GUI to see into the process. You can see that. I don't know if I can make it larger. I hope you can see that. Here you see all the applications that run in there. They're pretty much isolated from each other. One of the applications is called rig, and there you see the supervisor structure that I've just mentioned. For instance, you see a structure, a part which is concerned with the Kafka group consumer part, and broad is the library that we're using. And now I can try killing one of those processes. I can just kill the main Kafka client here. If I do that, you see in the top left corner that it exited because there was a failure. It tells you the last message and the state the process was in when it died. And you see also that the partition got reassigned to the other client. But now it has restarted everything, and you see that here, rig broad client is up again. The supervisor has catched the error, has catched the fault, and restarted everything in a sane state, just like he would restart, just like if the application would have been restarted, but only that part that actually died. And then you see it's up again, and it again got the assignment is now currently with the other one. So this is what the supervisors are for, and this makes the system very resilient to failure, to faults, because there are a lot of transient faults in a distributed system, like network connections might fail or stuff like this, stuff that you cannot really foresee. So it's good to have a system that's built on the assumption that everything can fail all the time. So this was Erlang. Now the question is, I said Elixir. What is Elixir and what is the difference? Elixir is basically a dynamic functional language on top of the Erlang VM and binary and also directly compatible with it. So for instance, you see here at the bottom ETS create, my ETS table. This is an Erlang method as called from Elixir. So you can directly call Erlang code from it. The advantage of Elixir, though, is that Erlang is famous for being hard to read and hard to write. For instance, you see here an example at the bottom where you try to replace something in a string and then make it uppercase. You have to use intermediate variable for that in Erlang, and you cannot reassign those variables anymore. So it's quite strange to write stuff in Erlang, and Elixir just makes it a very pleasant experience. It is kind of Ruby-ish, and it has simple syntactic sugar that's just nice to write, like the pipe operator. It has no monads, and this is by design. It tries to be a very simple functional language and very explicit in what it's doing. You still have meta programming and can write your domain-specific languages in it. You have data polymorphism and module polymorphism, and it also comes with a very capable build tool. And then, so this is Elixir, which basically a better way to write Erlang programs. Let's say it like that. Then you have the Phoenix framework, which we heavily rely on. It's a web framework written in Elixir, and it has two modules that we use heavily and rely on heavily. One of them is the pub sub module, which is usually when you send messages in Erlang, you always send from one actor to another. And if you want to do that in a publish-subscribe manner, like not sending one-to-one, but to many, then you can use this module. So this is all that it does. Everything in Erlang is around the idea that you're doing one thing and one thing well. So the modules are also very isolated and following this idea. Then the other module that we're using is presence. And this one is interesting because it's an in-memory key value store. It's eventually consistent over the cluster. And it's using JWTs, conflict-free data structures under the hood. And we use that for pretty much everything that we store in there. So for the connection state, for finding out which devices are connected where, and for the blacklist, and for the API configuration, everything. So we don't have any state on disk. Everything is in memory. And everything is eventually consistent and latency optimized. So to summarize this, as I just said, in memory only. This also means that we have no external dependencies. So when you deploy rig, you can't just deploy rig. You don't have to deploy Redis as well or any of the other stuff. And also if you want to scale out rig, you just have to scale the rig instances. You don't have to worry about scaling the database underneath it. And I also want to point out that I think, I know this is a Java conference, but I still think that Elixir is awesome to build software in, especially, I mean, it's probably not for every kind of project, but for a project like this, it's just perfect. We managed to implement all the features that we wanted to have for our 1.0 release in less than 600 single lines of code. And this is because much of the heavy lifting is done by the underlying virtual machine and Erlang and OTP, that's the Erlang framework, and Phoenix and all that kinds of stuff. So let me end this talk by talking about the roadmap. I was very, very quick. So where we want to go from here, we still don't have a logo. We have open sourced under Apache 2 just this morning. And we're still in the process of performance and production hardening. We want to do security tests on it. We're also working on a new join session API. This is the feature I've mentioned earlier with with having privileged users that can listen to the messages of other users. We want to have an API for that, such that your microservices can actually decide, okay, this user, we checked his privileges and he's allowed to do that. One use case for this could be a support user. Imagine you have a product where you have a lot of customers that where something goes wrong in their UI and they call your help desks and they want to know what they're doing wrong, and then your help desk user might just be able to spawn the same UI state and also listen to the same events, so he sees the actual keystroke that the user is doing. This is something that's possible with this. We're going for HTTP 2 support. We don't have it quite yet. At the moment, as I said, we have servers and events. No, I didn't say that. We have servers and events and WebSockets with a long polling fallback. So these are the transports that we have currently implemented. And at the moment, we are only supporting Kafka as the message broker, but thinking about other message brokers, supporting other message brokers as well. Also, login mechanisms. And this is the most important part, your idea. If you think that this project is interesting, and I know that loads of people I've spoken to here at the conference have told me that they were implementing something similar for at least one of their clients, because this is a very common issue. And still, it hasn't been, so far, there is no generic open source solution that you can just take and deploy with your microservices and have this feature. If you're interested in it, and if you have ideas, and if you just want to take a look at the Elixir source code and see what it's like, please just check out the GitHub repository. As I said, it's online since today. there is also more description and description on how to configure it and stuff like this. So having said that, I want to thank you for your attention, and we have loads of time for questions. And I also have a lot of architecture diagrams in the appendix if you're interested. Thank you. Any questions?
I can answer that one. So the question was, did you consider using Go? Yeah. In the final list, we had Go and Elixir essentially, because Go has has this very lightweight function model, and a lot of the applications that target a similar model are written in Go. Also, like databases and stuff like so. If you look at a pretty fancy thing like CockroachDB and so on, it's all done in Go. We had a very thin majority in the final voting for Elixir. By the way, the very first version of it was written in Node.js, which naturally didn't like scale out. Then they used the socket.io, and then they added then we added Redis to it, but that really didn't work out so well. We also had a small trial run once with Java, but not yet with an actor model. Yeah, that's essentially the tech story. But in the end, microservice paradigm and especially containerization and Docker to the rescue. I mean, in the end, you will just have a Docker container and you just boot it up, and you then tell Kubernetes, which essentially won the war for who has the best container scheduling mechanism, that you want more instances, and it will connect. So that is our aim. And we will tune the application appropriately if we need to change anything to get that goal.
That's also one thing I would like to stress. If you consider using it, you don't have to touch any Elixir or Erlang kind of stuff. It's configured using standard JSON, and you just spin up, as you said, a Docker container, and that's it. You don't even have to care in what it's written if you just want to deploy it.
Yeah, it is like completely neutral in that regard. All you have to do is you have to send JSON messages to Kafka. So essentially you send a JSON to Kafka, and within the JSON you essentially have the outside object and then the inside object, and in the outside object you say which customer is it, like the name, like for example Kevin, or whatever your system uses as an identifier, and then the inner object essentially is the payload, like I did a transaction or I did whatever. Now the rig is not concerned with what your JSON actually says. It just needs to find out which user is it, then it will look up which user it is, and it will push it out. And especially if you use server-sent events, you can subscribe with pure web technologies, no dependency to Phoenix, Elixir, whatsoever. It is super clean from the surface area that you have. And we also plan to, in general, do extensions in a way that you don't have to write any plugin that you throw into it. We think that does not really fit the modern microservice connotation. We take a little bit of inspiration there from Kubernetes, in that we just provide an API that allows you to do something. Like, for example, the subscription, that a support user just simply goes there, you call the API and you say, subscribe me, the support, to whatever Kevin is getting. And then you can essentially see what is going on. We have that stuff running, but not yet with that nice API.
There is also one thing that made it easier for us to choose Elixir over Go, which was the distribution primitives, and also the way we envisioned how it would work. Like, we wanted to have one tool that does one thing well and runs all the time. For instance, I forgot to mention that before, one of the problems when you have your WebSocket connections or SSE connections directly to your backend services is also, how do you upgrade those services without impacting the user? And you will upgrade those services all the time because they contain business logic. But in this case, when you have Rick holding the connections, you don't have to upgrade Rick that much. because it doesn't really change. It does one thing, and it does that all the time, and there is no business logic that you want to upgrade. Why would you change that? So your connections don't go down. You don't affect the user by upgrading your backend services.
Yeah, you can kind of upgrade your backend without destroying the running sessions and without caring about them.
So we wanted to have software that is also very, I've mentioned the 600 single lines of code. We wanted to have software that's really very stable and small and not very complicated, nothing that could fail. And if it fails, we have the supervisors. So the language and also the runtime system gives us a lot of primitives that are useful in that regard. For instance, if you have another node coming up, it will just connect to all the other nodes and everything will just work out. And we don't even have implemented that ourselves. It's just the Erlang runtime that works that way. When Ericsson designed the language and the runtime back in the late 80s, it was designed for having telephone switches, and they were designed to run 24/7 all the time. And if you have a new switch, you just plug the cable in, and it should just work. And this is exactly what we wanted to achieve here, without having to code it ourselves, because this way we can do mistakes.
Very lengthy answer to answer Go versus Elixir.
Yeah.
Other questions? No? Probably everyone is already tired.
Are there any features that you would love to see in such a system, or do you think that this system isn't usable at all?
Everyone's asleep.
Who has implemented some kind of event pushing in their applications at least one client?
1, 2, 3.
One of you.
Yeah.
How did you do it?
Well, we chose Reactive as the event host, pushing it back through an API gateway and use Nginx with a Lua plugin actually.
RabbitMQ
So
Nginx with Lua. Wow, nice one. And then Lua kept the connection, or okay.
And it validated the tokens of the JWT with a
Aha, so Lua did the JWT token validation, so a similar job like here, and then ran with an Nginx plugin and got it from RabbitMQ. That's a nice one. I mean, I don't know how exactly then to scale that one out, but yeah. Well, cool. Important message, of course. Accenture also in Belgium is, of course, hiring. And we're not only doing boring stuff, we're also doing pretty cool stuff, or at least we believe that it is cool stuff. But yeah, thank you.
Thanks very much.